In particular, I'm talking about a paper we recently submitted on looking at the elevated AGN activity as galaxies approach the quenching threshold that Sandy just talked about. So this is work that I've been doing closely with Guillermo Barro, Sandy, and Avishai Jekyll and Rachel Somerville, as well as a large cast of characters in the Canvas collaboration. So, as we've heard several times over the past couple of days, one of the key properties of passive galaxies in the early universe is their compact size. This plot shows the evolution in the effective radius as a function of redshift for passive galaxies in red here and star-forming galaxies in blue from Arjen van der Waals' 2013 paper, just indicating that these passive galaxies are 4 times as compact as their at high redshifts as their star-forming counterparts of the same stellar mass. And so it's very likely that a large fraction of these passive galaxies, these so-called red nugget galaxies, formed at an earlier epoch when all galaxies in the universe were more compact. However, if you want to quench a star-forming galaxy at any given epoch and quickly transform it and move it onto the red sequence, we need to actually transform its morphology so that it agrees with the size-mass relationship for passive galaxies. And so this has led to the idea of quenching that Avishai and Sharon talked about earlier today, this idea that these extended gas-rich galaxies will undergo dissipative collapse as a result of gas-rich mergers or violent disk instabilities or counter-rotating streams that will build up the stellar mass of these galaxies in their core and effectively reduce their size. Now, we think we've identified galaxies that have undergone this compaction in the form of compact star-forming galaxies, or these so-called blue nugget galaxies that Guillermo identified back in 2013. Despite their name, these galaxies are extremely red because they're dust-redded, but nonetheless they're star-forming. And the way we find them is that they are star-forming galaxies that obey the size-mass relationship for passive galaxies. And that's what's shown here. It's the effective radius versus stellar mass. And this red line is the size-mass relationship for passive galaxies at redshift 2.25, and these blue points are star-forming galaxies that appear to be structurally identical to the red nugget galaxies. Now, one of the key properties of these blue nugget galaxies is that they're short-lived. The blue nugget phase, it's estimated that it only lasts about 500 million years, about 500 million years. And we get this from ALMA observations that indicate there's extremely short gas depletion timescales in these galaxies. They have star formation rates on as high as 700 solar masses per year. And then, based on simple number density arguments, it appears that these galaxies need to quench on a timescale of several hundred million years in order to explain the increase in the compact quiescent population over time. This is the plot from Peter Van Dakke's 2015 paper showing the number density versus redshift for quiescent compact galaxies and for star-forming compact galaxies. And we find that the quiescent compact population increases, the number density of these galaxies increases at the expense of the compact star-forming galaxies. And in order to replicate this, we basically need an extremely short quenching timescale, 500 million years for these galaxies to move away. So, if we find a blue nugget galaxy, we have a pretty good bet that that galaxy is going to quench relatively soon. And this is one of the reasons why I call these galaxies the direct progenitors of the red nugget galaxies, simply because their quenching timescales are so short. Now, despite the fact that this phase is short, it actually has an important role in building up the stellar mass of the red nuggets. It's actually estimated about 30% of the stellar mass in the red nuggets are actually built up during this short blue nugget phase. And so a substantial amount of bulge buildup is occurring in these galaxies. So as you might expect, given that there's a black hole bulge relationship, that this might indicate we need elevated black hole growth in these galaxies as well. Now, to kind of highlight how the blue nuggets are actually, or these compact star-forming galaxies are related to the red nuggets, here I'm plotting the dust-corrected color as a function of versus the surface density of these galaxies, the density measured at the effective radius. And here, everything above this horizontal dashed line can be considered quiescent, so our red galaxies up here, and everything that is to the right of this vertical dashed line can be considered compact. And in this plot, I'm color coding points based on their Kocevski index. So blue disks are blue and spheroids are red. And the physical size of the symbol relates to the effective radius of the galaxy. So compact galaxies sit to the right and extended galaxies sit to the left. And in this phase space, red nuggets sit up here. They're effectively the reddest, most compact galaxies that we see at high redshifts. And blue nuggets live directly below them. They're this star-forming population that appears to be just as dense as the red nugget population. I should have pointed out this is a redshift of 1.4 to 3, and I'm doing a stellar mass of 10 to the 10 and above. So we're only looking at very massive galaxies. But the key point away from this plot is that these blue nugget galaxies appear structurally to be identical to the red nugget galaxies. All we need to do is shut down their star formation activity, and these galaxies will migrate up and join the red nugget population. Now, in the compaction scenario, these blue nuggets are, because they're quenching on a relatively short time scale, they need to be replenished by compaction. So essentially, you're taking extended star-forming galaxies from the left here. They're undergoing dissipative collapse. They join the blue nugget phase, and on a relatively short time scale, they quench. And this L-shaped curve, this L-shaped curve is the result of gas exhaustion plus feedback processes will cause this to quench. So here's a model from Lauren Porter's 2014 paper, just where they've identified in SAMs a handful of galaxies that are experiencing compaction and then quenching. And this is, again, is plotting specific star formation rate versus effective density. And these galaxies move over. At this point in the SAMs, energy is injected to get these galaxies to quench, and they quickly migrate up and join the red nugget galaxies. And these, as Joel is pointing out, these SAMs do include AGN feedback in there, and that energy energy injection is needed to get these galaxies to rapidly quench. So this is a more detailed view of this that we've seen already. This is modeled galaxy evolution tracks from the Vela simulations for 8 galaxies that undergo wet compaction. Again, we're plotting specific star formation rate versus density. Here we're measuring the density within the central 1 kiloparsec, so sigma 1. These galaxies undergo wet compaction. They reach maximal compaction at where these squares are indicated. And then, again, as a result of gas exhaustion and feedback, these galaxies will actually start to reduce the star formation rate and move up this quenching pathway. So this classic elbow shape, this L-shaped curve. So one of the things we wanted to do was check whether we actually see any evidence of elevated black hole growth or AGN activity right where these simulations tell us that energy injection is needed in order to quench star formation and move these galaxies up to the red nugget regime. And so that's what we set out to do. So we did this using all 5 of the candles fields. So we have size measurements for all 5 fields where we have the effective radius and now sigma 1 and sigma effective radius. And we identified, or we selected our compact star-forming galaxies based on the effective radius, their surface density at the effective radius versus stellar mass, and we simply selected star-forming galaxies that lie within 0.3 decs of the sigma mass relationship for passive galaxies, and that's what's shown here. These are the blue galaxies. These star-forming galaxies are shown in blue. The passive galaxies are shown in red, and the sigma mass relationship is this dashed line. And we've selected our massive compact star-forming galaxies as these green sources. Anything that lies 0.3 decks below this, this ridge line for our passive galaxies. And we identified AGN in these fields using Chandra observations. We now have deep X-ray observations in all 5 of the candles fields, including the UDS, which we actually just submitted a paper on our X-ray point source catalog in the UDS, which should be out relatively soon. So using these observations, we have a sample of about 1,500 AGN in all 5 of the candles fields. And so we took a look at their host properties. So this plot shows, again, the rest frame U minus V color as a function of surface density in various redshift bins going from redshift 3 down to redshift 0.5. We see at the highest redshift bins, these star-forming galaxies, diffuse star-forming galaxies, and the scattering of compact systems. As time evolves, we see the red nugget populations start to appear in large numbers. We see some compact star-forming galaxies down here, and then at later times, the compact star-forming, or the compact quiescent galaxies start to migrate to larger radius as these galaxies start to puff up, presumably as a result of dry mergers. Now here is where, actually, I'm ahead of myself one step. Here where the extended star-forming galaxies live, the compact star-forming galaxies, the compact quiescent galaxies, and the extended quiescent galaxies, these 4 quadrants. And this is where the X-ray AGN live in this diagram. So we find that the X-ray AGN are scattered throughout the plot. However, you can start to notice that they're overrepresented in the lower right-hand quadrant, essentially where the compact star-forming galaxies are. They're, as a fraction of the total number of galaxies, we see that the AGN tend to live in that lower right-hand quadrant more often than anywhere else. We can quantify this a little bit better in a second. This again is that same dust-corrected color versus sigma, and we just to remind you, we think that we need AGN feedback in this lower right-hand quadrant, right where these galaxies are going to end up quenching. And this is what the AGN fraction looks like as a function of in this phase space, and this is what Avishai showed a little earlier today. Dust-corrected color versus density, and the color scale here indicates the AGN fraction at each one of these hexagons. We find that about 40% of the compact star-forming galaxies host an X-ray luminous AGN, and that's about 5 times more often than in any other of the quadrants in this diagram. In fact, the extended star-forming galaxies of similar mass only host AGN about 7.6% of the time compared to about 40% of the time. And again, we're looking at sources with masses greater than 10 to the 10 in the redshift range 1.4 to 3. So substantial increase in the AGN activity as galaxies approach, again, this quenching boundary that Sandy talked about in the last talk. These galaxies are basically reaching the ridgeline. These are star-forming galaxies that are reaching the ridgeline of the passive, defined by the passive galaxies, and all of a sudden their black hole growth starts to increase significantly. So just to illustrate this again, this is Avishai's tracks from the Vela simulations, and then on the right here I'm also showing tracks from Rachel Somerville's SAMs, where here she's plotting sigma to the effective radius, measured at the effective radius. And again, we see this L-shaped curve, and we're finding this peak activity just where the SAMs tell us we need energy injection to get these galaxies to move up. Now, we've heard a lot about sigma 1, so I just wanted to show you guys how the results change if we use sigma 1 as opposed to sigma measured at the effective radius. This is a plot from Guillermo Barros' 2017 paper that Sandy already showed, just indicating the difference between the effective radius versus mass versus the central density versus mass. And we find that the central density better correlates with mass, and as we'll see in a second, better correlates with quiescence as well. So we can do exactly the same analysis we just did, but using central density to select our compact star-forming galaxies, and we find pretty much the same result. Here is dust-corrected color versus sigma 1. We get a nicer L-shaped curve. Effectively, these extended quiescent galaxies have moved over to the right-hand side of the plot, because now we're measuring their central density. And again, color-coded by Sircik. And here is what we find for the AGN fraction. Again, using sigma 1, we find that the AGN fraction peaks in these compact star-forming galaxies. And in fact, we find a very nice correlation between sigma 1 and the AGN fraction, the observed AGN fraction. And that's shown here. This is the AGN fraction, X-ray detected AGN fraction as a function of sigma 1, and we see this dramatic increase as we go out to the most dense galaxies. We find, again, about 40% of these compact star-forming galaxies with the sigma 1 values are experiencing an active growth phase. Now, it is expected that the AGN fraction is going to increase as you go to high stellar masses, and that's simply a selection effect. You're going to have a more massive black hole, and you require not as much accretion to basically exceed your flux limit of your X-ray observations. And what's shown here in gray is basically what we expect the AGN fraction to do as a function of mass alone, independent of sigma 1. And we do see that some of this increase is just related to mass, but at the highest densities, we find that the AGN fraction still exceeds what we expect simply based on the mass dependence alone of the AGN fraction. Right. So what can we draw? What conclusions can we draw from these observations? Well, at the very least, it's telling us that compaction results in an increase either in the duty cycle of these AGN or the accretion efficiency. either one of these would produce what we're seeing. Now, if we go to our deepest sample, and that's in the Good South field where we have the 7 megasecond X-ray observations, we can actually produce a volume-limited sample of galaxies and measure their age infraction, and that sample turns out to have an age infraction about 56%. And based on the quick quenching time scale of the compact star-forming galaxies, we can then infer a duty cycle for these AGN of about 280 million years. They're on about half of the time, if we believe this fraction, 56%, and a quenching timescale of 500 million years. And so, based on this, and based on the X-ray the median X-ray luminosity of these sources, we can figure out how much black hole mass is actually accreted during this phase. And it turns out to be that it's about 31% of the final black hole mass in the red nugget galaxies is accreted during the blue nugget phase, based on the AGN fraction and the AGN luminosities that we measure at these galaxies. So this matches extremely well with the amount of stellar mass built up, measured in a completely different way. This is what Peter Van Dokken reported in his 2015 paper. He found that about a third of the stellar mass of the red nuggets was built up during the blue nugget phase. And so we're finding that the black holes are actually growing in lockstep with their bulges, which is exactly what we might expect. Now, I mentioned earlier that compaction is not the only way that we can produce compact star-forming galaxies. In fact, they may simply have formed at an earlier epoch when all galaxies were more compact, were smaller. And so this is what I've been referring to as the early formation model versus the late compaction model. The early formation model is just basically the progenitor bias scenario. But in the early formation model, I guess the best plot to look at here is probably this one, stellar mass versus redshift, and this plot shows density versus redshift. And in the early formation model, most of the central mass density is put in place at relatively high redshifts, between 3 and 5, and then it plateaus off until you see these galaxies at a redshift between 2 and 3. In the late compaction model, most of this central density is put in place at late times due to a compaction phase. And the same scenario happens with the black hole growth. In the early formation model, the black hole growth occurs at high redshifts and then drops off as you approach redshift 2. And in the late compaction model, there's a spike in the growth rate at late times. And so our model, even though we haven't tested on redshift 3, our observations seem to favor the late compaction model over the early formation model in this case. And finally, the observations hint at a possible role of AGN feedback in the quenching process. Even though these galaxies may not be driving extreme outflows, quasar mode outflows to actually kick gas out of these systems and actually drive the quenching process themselves, it could very well be that this rapid growth in the black holes during this phase is actually setting up future preventative feedback in these systems that will heat the halos and prevent renewed star formation in these systems. This is something that we're going to have to follow up. And so with that, let me put up my summary. I will say that we do have future observations with MOSFIRE to look for outflow signatures in specifically these galaxies, and so that's something we're going to be following up. Yesterday, Mauro and Steve asked the question, do we see smoking gun evidence for AGN feedback? I don't think we see smoking gun evidence, but we're starting to find the bloodstains in the trunk. And so I think there's the circumstantial evidence is starting to be built up that there might be some connection. And what I really like about these observations is that they agree really nicely with Sandy's model that as these galaxies approach the quenching boundary, reach this ridgeline. In this paper, we use 0.3 dex. Sandy quoted 0.2 dex. But either way, we're finding that as we approach that ridgeline, the AGN fraction starts to increase significantly and more than you would expect simply based on a mass dependence of the galaxies. Okay, I'll stop there.
Questions?
Need more coffee.
I'm going to ask one myself.
Sure.
You sort of put in favor of the late compaction that you close it like, that's late would fit better.
Mm-hmm.
But I think you could sort of, in the early formation model, you could just say, because they have obviously star forming, that there's something sort of that has replenished the gas supply in one of these early forming ones that feeds the black hole as well. So I wouldn't sort of see this as a link in terms of favor of the lake compaction.
Sure. Okay. I should say, I mean, this is something we can directly test with JWST, of course. We can go in and look at registers 3 to 5 and see if we find elevated black hole growth in the precursors of the blue nuggets forming earlier. That's right.
Can you say anything of the age of the stellar populations?
Yes and no, although there's intense star formation, so the systems appear young, all the blue nugget galaxies. The red nugget galaxies, of course, they appear old, even at that point, when we observe them at redshift 2.
What's unusual about the AGF that are not that old, like
yeah, it's a good question. No, I mean, they look like your standard, they're bulge-dominated disks. They tend to be bulge-dominated disks. They could be fed stochastically through secular processes, some other mechanism other than compaction. Yeah. There's some quiescent galaxies in there as well. As Tao Wang mentioned, the AGM fraction of the quiescent galaxies is non-negligible as well. Yeah. Well, yeah, it depends on how you select your galaxies. That's right. Yeah.
You seem to recall that if you look at the Vanderbilt plots, and he shows you the red galaxies and the blue galaxies, if you look at Z of 2, you can see that about 30% of the quenched galaxies, the objects that he calls quenched, are sitting at large radius, not below the dividing line, would not be called nuggets. Have you ever looked into them? You look at the
extended quiescent galaxies. No, we haven't. So there are a substantial fraction. I mean, it depends how you define extended. Using sigma 1, there's very few of them, and the AGM fraction is not that great there. But using effective radius, they do have quite a high AGM fraction, about 10% of them.
Okay.
Yeah, but I haven't looked at them.
Please.